Welcome back to chapter 4, where we will talk about the composition of functions. So today in section 4.3 we will talk about two functions. The first one's from A to B and the second one from B to C. So if we do it as an arrow diagram, this is what we will get. This is A, and the function f goes from A to P, and the function g goes from B to C. Now, the composition of function is a way to go from the first input to the last output through f and g. So what is the composition of two function? Of course, is first of all is a new function. We denote it by g circle f, and it will take as an input A and as an output B. Now let's see how this function will work. It will take an input x, so as usual x will start from here. If we take it with f, it will go to f of x. If we take it with g, it will go g of f of x. So here x would be mapped into g, and inside g we write f of x. This is the composition of functions, and this is how it works. If we just try to summarize it here, we write it as g circle f for an input x is equal to g, and then we write f of x inside it. So this is the composition of function, and this sign here, this circle here, we call it composite. So we say G composite F. Of course, there is a note that must be written in red, so keep it in mind. This note here is that G circle F as a function is not the same as F circle G, because the input and the output maybe are not the same. It's a different function, so just keep this in your mind. And what we will do next is we will solve some theorems up here. So we have some theorems that we need to solve. So we have theorem number 1, which tell me some information about injective, surjective, and bijective. So if you didn't see the previous video, I would recommend that you pause here, watch the video about injective, surjective, and bijective, because we will do now theorem number 1. So for theorem number 1, I will start with the first one, which is I will assume that f and g are both injective, and I will show that g circle f is injective. So here I will use direct proof, assuming this is p and this is q. So p implies q, or if p then q. So the idea is we will assume f and g are both injective maps, and the required, we need to show that g circle f is injective as well. Now how do we prove that G circle F is injective? If you remember, we will do the direct proof approach for proving the injectivity. So I will just go ahead and assume I have two inputs give me the same output. So G circle F of x1 is the same as G circle F of x2. Of course, this has a meaning. This means G of, let me now write it as in a different color if you allow me. Sometimes writing a different color help us see what is going on. So this is G of this, and then we have G of f of x2. Now, because G is injective, if we have two inputs are equal, whatever inside will be also equal. This is because G itself is injective. So here we have f of x1 will be definitely equal to f of x2, and the reason why because G is injective. Now, again, remember that F is also injective, so whatever, if 2 points, they have the same output, it means whatever inside have the same input. So this means that x1 definitely will equal to x2, and this is exactly what we want to prove, and the reason for this is F is injective. So a very easy, very direct, straightforward proof for proving that if 2 functions are injective, their composite is also injective. However, part 2, I will just leave it for you as an exercise. It's a very good exercise to try to prove the surjectivity using the surjectivity of F and G. And of course, part 3 is just we combine part 1 and 2, because if both functions are injective, this is part 1, surjective, this is part 2. So we get from part 1 injectivity, part 2 surjectivity, which means everything together is bijective. And this is exactly theorem number 1. Now let's go to theorem number 2, and let's ask ourselves the opposite question. What happens if this is injective? Do we get the other direction? Do we get that each one of them is injective? The answer would be no, but the only information we know is as follows. So if you look at theorem number 2, here we have that the composite is injective. The only information we know and we are sure of is that F is injective. Similarly, if the composite is surjective, the only information that we might know is that G is also surjective. So part 1, I will leave it as a homework, but part 2, let's do it together about the surjectivity. So we need to prove that G is surjective. So sometimes a quick arrow diagram can help me finding out what is going on. So this is B, this is C, and I want to show that G is surjective. Remember, to show G is surjective, we must take something, I will call it Z in C, and as a required from me, I need to find an input is mapped to Z. So we need to find Y in B such that G of Y equal to Z. That's the meaning of surjectivity. I will give you an output, find for me an input that mapped to it. Now, what do we know? We know that if we consider the composite, which means A, F, if we consider the direct way going from the first one to the last one through the composite, we know that G circle F is surjective. That's for sure, we know it. So that means there exists an X in A that mapped into C. So G circle F of X equals Z. That's for sure, we know it. Why? Because the function is surjective. The yellow one is surjective. Okay, so far so good. I think now the problem will be solved by itself. If we write this one, this is just G of F of X equal to Z. Okay, now look at what we need to prove in the yellow. We need to prove that G of something equal to Z. Can we know what is Y? So the last step in the proof, set Y to be equal f of x. Of course, this belongs to b, so we are done. So we get f of x. Now, clearly, g of y, which in fact it is g of f of x, equal to z by this one. And that will solve the second part of theorem number 2. And this is all what I want to say about the composite of functions. Thank you for watching. Please